Okay, I want to go over Trapezoids and Kites. This is 6-6 of our textbook, Trapezoids and Kites. It's on page 389. And a lot of the things about trapezoids and kites are pretty simple. We just finished up before the holiday. We went over quadrilaterals. These are the last two quadrilaterals. They're part of that polygon family tree that I gave you, and you'll see all those properties on there as well. But let's go ahead and go over what they have here in the book. There's some terms that need to be on your vocabulary for chapter number 6 here in the middle of the page. Our essential understanding will be the angles, sides, and diagonals of a trapezoid have certain properties. We're going to talk about those properties. Now, the first thing is, what is a trapezoid? A trapezoid is a quadrilateral with exactly one pair of parallel sides. Now, we have to put in that exactly one, because if you say that it has parallel sides, then it could sound like a parallelogram. So exactly one pair. Parallelogram has both pair of opposite sides parallel, or two pairs of parallel sides. This has exactly one. So that's the definition of a trapezoid, quadrilateral with one pair of parallel sides. The parallel sides are called the bases. So you have a base and a base, two bases. Now, all trapezoids are not going to be sitting on a base. They could be turned the other way, so they're sitting on the leg. It's just the parallel sides are called the bases. See, we could turn the book 90 degrees, and these would still be the base, even though they're not sitting on that base. So the parallel sides are called the bases. The non-parallel side are called the legs, just like a isosceles triangle. We call them legs. We also talk about down here, you'll see isosceles trapezoid. So the legs are the non-parallel sides. The two angles that share a base of a trapezoid are called base angles. So it's going to have two pairs of base angles. This angle and this angle are base angles, and these two are also base angles. All right, so we have four, or all the angles really are base angles, because they share a side with a base. Okay, and a trapezoid has two pairs of base angles. Now, when we get to an isosceles trapezoid, and that's where a lot of our properties are going to come in. For just a trapezoid, we just know that it has exactly one pair of parallel sides. The non-parallel sides are legs. The angles are referred to as base angles. But with an isosceles trapezoid, it's a little more. An isosceles triangle is a triangle with two congruent sides. An isosceles trapezoid is a trapezoid with legs that are congruent. In an isosceles triangle, the two congruent sides were called the legs. And in an isosceles trapezoid, the two non-parallel sides, which are the legs, they're also congruent. So this is an isosceles trapezoid. Here over at the right, we call it ABCD as an isosceles trapezoid. It says the angles of an isosceles trapezoid have some unique properties. Now, they are still base angles. Angle A, D, C, and B are all base angles. But now that it's an isosceles trapezoid, base angles A and D will have something in common, and base angles B and C will have something in common. And that's our first theorem down here. And it just simply says, if a quadrilateral is an isosceles trapezoid, then each pair of base angles. See, base angles, remember, by definition, the base angles, it said the two angles that share a base of a trapezoid are base angles. So these two share a base. Those are base angles. These two share a base, so they're base angles. But it's like all four angles are base angles, but it's pairs of base angles. So in this one, if a quadrilateral is an isosceles trapezoid, then each pair of base angles are congruent. So that means angle T is congruent to angle P, and angle A is congruent to angle R is congruent to angle A. I was saying it backwards. But that's trapezoid TRAP. R and A are base angles that are congruent. T and P are base angles that are congruent. It's really kind of like you took an isosceles triangle. If you went on up here like this, you ended up with an isosceles triangle. So these base angles would be congruent. And we've chopped it off, and now these, two base angles are also congruent. Now, something you need to know too, this angle is congruent to this one. This angle is congruent to this one. But these two angles, T and R, are special too. See, since the lines are parallel, they're same side interior angles, so they have to be supplementary. So angle T and R would have to be supplementary. Angle P and A would have to be supplementary because they're same side interior angles. So that's something to keep in mind too when we're trying to find the measure of some missing angles. Here's some example or sample problems we're going to have. They tell us that this trapezoid is an isosceles trapezoid. Of course, they've marked the two legs congruent for us. CD and EF are congruent, so it's an isosceles trapezoid. They also mark the two bases parallel. All right. So if angle C is 65, then its base angle, angle F, would also be 65. And those are the only two you have. But remember, angle C and D must be supplementary. and angle F and E must be supplementary. So all you have to do is say 130 or 180 minus 65, and angle D would be 115. Now over here what they did is said angle C and angle D is equal to 180. Like I said, they're same side interior angles. If angle C is 65, then angle D will make up the difference, so angle D had to be 115. So that means that angle D is 115, angle E is 115, and then these two were both 65. So you're going to have two pairs of congruent angles because the base angles will be congruent. But then this base angle and that angle will always be supplementary because the lines are parallel. Okay, like on this next picture, notice this time these are the parallel sides, they're the bases, even though it's not sitting on the base like the one above, these are the base angles. So if these are the two bases, these are the legs. So if that one's 106, angle S would be 106 because that's a pair that are congruent. Then 106 from 180 tells us that these two would have to be 74 apiece. Okay, so it's real simple. And then all the angles added together have to equal to 360 degrees because remember it's a quadrilateral. Okay, next problem. We'll look at this one kind of carefully. It says find the angle measure in an isosceles trapezoid. So it's the same thing we were doing at the top, but this is what I was talking about a moment ago. See how this is an isosceles triangle, but by drawing this segment now there's an isosceles trapezoid. Okay, so that's what I said about cutting it off. Now I said there are 20 of these congruent isosceles trapezoids in this fan. Okay, the second ring of the paper fan shown are the at the right consists of 20 congruent isosceles trapezoids that appear to form a circle. What are the measures of the base angles of the trapezoid? So first what we need to do is in this triangle, okay, this triangle, the white triangle, if there's 20 of them, then that's 360 divided by 20. So they tell us the measure of angle 1 is 18. All right, so if angle 1 is 18, then we can find these, because that's an isosceles triangle, we can find the base angles. So 360, well, what they did, they said 18 plus x, because these two would be both x, because it's an isosceles trapezoid, these two base angles have to be congruent. They said x plus 18 has to equal to 180, or 18 plus 2x equal to 180. Subtract 18 from 180 and divide by 2, and it's 81. So x and this angle, these are both 81. And angle y has to be supplementary to this one. So 81 minus 180 would be 99 for angle y. So that's how we would do that. First, you had to find in this isosceles triangle what the vertex angle was by dividing by 20, because there were 20 of those. Remember, it said there's 20 congruent isosceles trapezoids, so that's 20 congruent isosceles triangles. That's how we were able to find x and its base angle, which would be the base angles of the isosceles triangle, and then we could find the other base angles by subtracting one of those from 180. So they were 99 apiece. Over on the next page, we have some more theorems. It says the quadrilateral, if a quadrilateral is an isosceles trapezoid, then its diagonals are congruent. Okay, so that means that from B to D and from C to A would be congruent. So just in any ordinary trapezoid, this wouldn't be the case, but if it's isosceles, then the diagonals are congruent. Okay, just remember that, and we'll use that later on. Then in the middle of the page, there's lesson 5. Said in lesson 5-1, you learned about a midsegment of a triangle. Now, we didn't do midsegment of a triangle at that time because we moved past chapter 5. That was one thing we'd have to go back to do. But a midsegment of a trapezoid is similar to one of a triangle. And in a midsegment of a triangle, it's just a segment that joins the midpoints of two sides of a triangle. And it's half the measure of the third side. That was the theorem in lesson 5-1. Well, here we have the midsegment of a trapezoid. It joins the midpoints of the two legs. Okay, so M is the midpoint of RT, N is the midpoint of AP. Okay, so MN is the midsegment. And the way it works, that midsegment will be parallel to the two bases because it joins the midpoints of the two sides. It's parallel to the two bases. Okay, and it's the average of the two bases. In other words, if you add these together and divide by 2, you would get this measure. So it says if a quadrilateral is a trapezoid, and it didn't say isosceles, any trapezoid, the midsegment is parallel to the bases, and the length of the midsegment is half the sum of the lengths of the bases. Since there's two bases, it's the average. Add them together, divide by 2. So it's half the sum of the two bases. So all three segments, RA, MN, and TP, are parallel, which means we're going to have same side interior angles, corresponding angles that are congruent in this picture. And also that its measure is half the sum. Now, a lot of times I do this a little different. I'm going to show you this example at the bottom, and I'm going to show you, yes, MN is equal to half of those two added together, and that's great if you just have numbers. You could just add these two together and divide by 2 to get that one. But a lot of times the problems are a little more than that, and let me show you the example they have here in the book. And I'm going to do it just a little different because you'll see me doing it differently when I'm doing the homework and everything, because I think it's much easier. Now, the theorem, it tells us QR is the mid-segment. You know, of course, that's telling me that this segment is screwed to that one because that's a midpoint, and this segment is screwed to that one because R is the midpoint. Since this is the average of these two, okay, then this is equal to half of their sum. You add them together and divide by 2, and that's what they did here. QR is equal to 1/2 of LM plus PN, half the sum, okay? It's the average. So they said QR, they put x plus 2 is equal to half of these two, substitute them in, you add them together, you get 4x minus 2. Half of 4x minus 2 is 2x minus 1, and that was equal to the mid-segment, which was x plus 2. So x is equal to 3. Now, what I said about doing it a little bit different, rather than saying the mid-segment is half the sum, well, it's the same concept or the same idea as if I just say 2 times the mid-segment is equal to their sum. Right? I mean, it's the same thing they did here. They just worked this problem out and then they divided this. Well, what if this were something odd and it didn't divide real well? Well, the best thing to do, rather than have this 1/2 here, is multiply by 2 on this side. Then you don't have to worry about taking half of something. It's much easier to double something than it is to take half. You can double an odd or an even number, but taking half, it needs to be an even number, unless you want to have more fractions. So when I set them up, rather than setting up this is equal to half of their sum, I double this, double the mid-segment is equal to the sum. So 2 times x plus 2 is equal to 4x minus 8. And it will work the same way. I just use distributive property, 2x plus 4 equals 4x minus 2. I'll subtract 2x and get 2x minus 2. I'm sorry, I'm left-handed. You can't see my writing until I move my hand. And then we'll add the 2, and I get 6 equals 2x, and divide by 2, x is equal to 3. So see, I got the same answer. It was the same answer, but this was much easier because you don't have to worry about taking half of something. Okay, for instance, if this, like I said again, if that would have been a 5x minus 2, then you got a whole another problem. Or you could just set it up this way and automatically multiply by 2 to move the half out of the way. But I just go ahead and say 2 times the mid-segment is equal to the sum of the bases. Rather than say the mid-segment is equal to half the sum, I say 2 times the mid-segment is equal to the sum, because it's the same idea mathematically. Okay? So you're going to see a lot of those problems in your homework, and that's the way I always set them up. 2 times the mid-segment is equal to the sum of the bases. Okay? Then over on the next page, another example of this. Of course, we have this problem at the top. We're supposed to find the measure of that segment. Again, I'm going to do it exactly the way I did the last one. I'm going to say 2 times 2x plus 11 is equal to the basis, is equal to 10 plus 8x minus 12. So double the mid-segment is equal to the sum of the bases. 4x plus 22 is equal to 8x minus 2. And then I'm ready to solve. Subtract 4x, 22 is equal to 4x minus 2. Add 2, 4x is equal to 24. Dividing by 4, and x is equal to 6. In a lot of cases, they'll ask you to find x, but then they'll ask you to go back and find the measure of the segment, so you just plug it back in. Since x was 6, if they want to find mn, 2 times 6 is 12, plus 11 would be 23. And that's how you would just substitute back in for x to find the values or the lengths of any of those segments. So that's mid-segment. Mid-segment, remember, it's parallel to the two bases, and it's half the sum of the bases, or double the mid-segment is equal to the sum of the bases. All right, and then next we have the last trapezoid, which is a kite. And a kite is a quadrilateral with two pair of consecutive congruent and no opposite congruent sides, okay? So it doesn't have opposite congruent sides, it has two pairs of consecutive congruent sides. If the opposite sides and the consecutive were congruent, then it would make it a rhombus, all four sides would be congruent. But it has two pair consecutive, one after the other, next to each other, congruent, and no opposite sides congruent. So that makes it a kite. And everybody has seen what a kite looks like, but that's the definition. And the theorem in the book, they only give us one theorem, but there's a lot more things about kites that they leave off. Let's talk about this real quick. Here's a kite, and it says if a quadrilateral is a kite, then its diagonals are perpendicular. Okay? Yes, its diagonals are perpendicular, meaning that they form right angles. Now, diagonals are definitely not congruent in that picture, but that's the only theorem they give us, but there's other things that we can look at and know that's true as well. Okay? In this kite, in a kite like this one, angle A and angle C are definitely not congruent. They're not the same. But angle B and D are congruent. Those two opposite angles will be congruent. A and C are not, but B and D will. And the only way you can do that is look at, it's actually the angle between the angles between the non-congruent sides are congruent angles. Okay? But there's not a theorem that says that, but it's true. Okay? Only theorem they give us is that the diagonals are perpendicular. They have the proof of the theorem about the diagonal being perpendicular down here, and that's fairly easy to prove too, because this is just like I said here, it's a kite, and they tell us the segments that are congruent. That's given. It says A and C lie on the perpendicular bisectors of BD. A and C on the perpendicular bisector of BD. So if it's on the perpendicular bisector, it's equidistant from these. Okay. And that proves that this has to be perpendicular by definition of a perpendicular bisector. It proves that they're perpendicular. That part of it's perpendicular. Let's look at some other examples. Let me show you again the examples and talk about the similarities, because there's a lot of problems just like this. They'll have a kite. This is a kite. They ask you to measure the angles. Automatically, we know angle 1 is 90 because the diagonals are perpendicular. Okay. They tell us that one is 52. Okay. That one's 52. Now remember, since it's a kite, this is an isosceles triangle, like that. This is a right triangle. Both of these are right triangles, and they're both congruent. Again, we don't have theorems that tell us that, but it would be easy for us to prove that. So then, if angle 1 is 90, this angle that's 52 and angle 2 have to be complementary. So all you have to do is you can say 90 plus 52 from 180 is angle 2. And that's what they did here. Got angle 2 is equal to 38. And then angle 3, because this is an isosceles triangle, and this is perpendicular to the base, then it bisects the vertex angle, because that's an isosceles triangle. So these two angles, this one and angle 3, will be congruent. Again, we don't have theorems. It's because it makes an isosceles triangle, and this is perpendicular to the base, that these two had to be congruent. Same way with this triangle here, down here, EFG. That's an isosceles triangle. That's perpendicular to the base. So these two angles are congruent. Okay? Or you could say angle F and angle D have been bisected by that diagonal. Okay? Now, that's not true for angle E and G, of course. These two angles are not congruent, neither are these two. Now, this one and this one would be congruent because they're base angles of an isosceles. See? But these two are congruent, and then these two are congruent. Okay, another picture. You got a lot of practice doing some of those problems in the homework assignment. Same thing, we got a kite here. Angle 1 is going to be 90 degrees. If this is 36, then angle 3 will be 36. Remember, because that diagonal is going to bisect these two angles. The angles between the two congruent sides, they get bisected. So that one's 36. And then 36 and 90 added together, subtracted from one. Either 90 plus 36 from 180 is angle 2, or because the acute angles of a right triangle are complementary, you can say 36 from 90, and that would be, of course, 54 degrees, angle 2 would be. So angle 1 was 90, angle 2 was 54, and angle 3 was 36. And then here's kind of a partial picture, like my picture that I gave you when I gave, or this family tree, the polygon family tree. It's similar to it because they're taking the quadrilaterals and they're breaking them down into pieces like that. If you look at that sheet that I gave you, of course, we have the kite and the trapezoid, and here are the properties of the trapezoid that we just discussed, and it's on that Papa Polygons family tree. A trapezoid has one pair of opposite sides that are parallel, exactly one pair of opposite sides parallel. The mid-segment of the trapezoid is the segment that joins the midpoints of the two legs. It's parallel to the bases, and the length equals the average of the bases. I say the average of the bases, it's equal, double that, it's equal to the two bases added together, or the two bases added together by 2 is the mid-segment. Either way you look at it, and that is the average because there's only two bases. And in an isosceles trapezoid, it said the non-parallel sides are congruent. That's the legs. Base angles are congruent, and diagonals would be congruent. And then I have the kite up here at the top, and I put a little more information here. It says 2 pairs of congruent adjacent sides. So these two would be congruent, and then these two would be congruent. 2 pairs of adjacent congruent sides. 1 pair of congruent angles. That's the ones between the two congruent sides. No, that's the ones between the non-congruent sides. This angle and this angle will be congruent always. And then the diagonals are perpendicular. So the diagonals are perpendicular like that. And then, of course, the isosceles triangle theorem helps us solve for a lot of other things. This diagonal also bisects these opposite angles. And you'll see that as you start putting the measures together. Even though they're not theorems in the book, that's the way it works. Okay, so the assignment is in teams, so good luck solving the problem.